All right. So entropy, or the second law of thermodynamics. First question we're going to talk about is what is entropy? And this presentation is going to be a little bit different in that I front-loaded our informational pieces, and then all of the sample problems are at the end. Okay? And because we just kind of have to deal with this all at once, it's not like we can introduce one concept, do a couple of sample problems, and then introduce the rest of it. So yeah, I front-loaded the information. Also, this is a little bit different in that I actually went through and already solved all the example problems on the slide so that there's not the disconnect between what I do on the board and what shows up in the slides. All right? So what is entropy? So here's a way you can think about entropy that really makes a lot of sense and really helps to make it simpler than what entropy actually is. And so you can think of entropy as a measure of how random something is. Okay, so a bedroom that is nice and neatly organized would be less random than a bedroom that is an absolute wreck. Right? That makes sense? Or a car that is assembled and all the pieces are in their proper places is less random than all of the individual parts not assembled. Okay? So a measurement of the randomness. Okay? So yeah, higher entropy equals more disorder. And this ends up being kind of weird when you start calculating and getting a mathematical representation of entropy or a quantification of entropy, because you want to see if it's a positive number. You're like, well, that's good, right? Because we're trained to think of as positive as good, because when you have a positive amount of money in your checking account, that's good, right? If you have a negative amount of money in your checking account, that's not so good. And I don't know if you guys have checking accounts or not, but if you have money at your disposal, if you have money in your pocket, that's good. If you owe someone money, that's not good, right? And so we have this idea of, if it's a positive number, it's good. If it's a negative number, it's not so good. But with entropy, it's actually kind of the opposite. A positive number of entropy means that it's getting more random, less organized. A negative number for entropy means it's getting less organized. And so, no, I'm sorry. So higher entropy, positive number, it's becoming more random. Negative entropy, lower number, becoming more organized and more structured. Yeah, this is a false wall. And so you can actually open up the entire wall and have one big lab. And so I think I was talking loud enough that the person over there wanted to make sure it was sealed all the way. And then the wall becomes soundproofed. But all right, so technically speaking, entropy is the number of ways in which you can rearrange all of the particles and to rebuild whatever that macroscopic object is. So again, with the idea of a bedroom, if your bedroom is just an absolute wreck, it's basically the number of ways in which you can arrange all of those particles to still have an incredibly disorganized bedroom, right? There'll be a lot of ways you can do that, whereas a room that's actually picked up and tidy, you have less amount of ways in which you can reorganize and still have a nice, tidy, well put together bedroom. Does that make sense? The car illustration is an even better one for that. If you just have a pile of all of the parts, there are a lot of ways in which you can arrange that in which you still just have a pile of parts, right? But if you have your car fully assembled, every part in its right place, there's only one way, maybe a couple of ways, that you can do that and still generate a fully functioning car. Make sense? Okay, cool. So the second law of thermodynamics comes in and is involved to basically say that the entropy of the universe is always increasing. So the entropy of the universe is always increasing. That is, the universe, which includes everything. Remember our discussion of systems, surroundings, and then together that's the universe. So the universe is everything. But yeah, so the collection of everything, the universe as a whole, is becoming less organized. It's becoming more random, less structured. That does not mean that individual systems cannot become more organized, less random. Right? We know that happens. right? Plants trap sunlight and use it to make sugars, right? Have you all done a bio class? Anybody in here not done a bio class, or at least not done some kind of a life science? So do you know what I'm talking about with plants making sugars out of sunlight? Yeah. So, well, plants will do that. And you're like, well, the second law of thermodynamics says that shouldn't be possible. It's not true. The second law of thermodynamics says that the entropy of the universe is always increasing. An individual system can become more structured as long as its surroundings become less structured at the same time. And so overall, your universe is becoming more random, less organized. Okay? So in order for the entropy of a system to decrease, that is, for the system become more organized, the system has to absorb energy. The system has to absorb energy, and at the same time, the surroundings need to become less organized. Okay, so let me show you what's actually going on inside of a plant. Okay, for those of you that haven't seen it. Here's the reaction of what we call photosynthesis. And so this is what's going on inside of a plant as it harnesses sunlight and makes these sugars, these fuel molecules. Okay? And so what you have here is you have 12 total molecules. Do you see that? We have 6 molecules of carbon dioxide. We have 6 molecules of water. You have 12 molecules. There's a lot of ways in which we can arrange that and still have 12 molecules of carbon dioxide and water, right? When you get over here, sorry, I left off a 6 here. When you get over here, we only have 7 molecules, right? We have one really big complex sugar molecule, and then we have 6 molecules of oxygen. So we went from having 12 molecules to having 7. We have fewer molecules. There are less ways in which we can arrange this and still generate the same thing. Make sense? More ways to arrange, less ways to arrange, right? And so this has basically gone the opposite. This is decreased in randomness. So our entropy would be negative here. It's less random at the end than it was at the beginning. And so the only way that this is possible is if what happens? According to our last point on this slide. The only way for this to happen is if the system absorbs energy. And it does. We call it photosynthesis because photo means light. What is it absorbing? Sunlight. It is absorbing energy from sunlight. That is the only way to make this happen. So your system can become more structured, can become less random as long as it absorbs energy in the process. And the surroundings become less organized. Which they do, because instead of having 12 molecules in the surroundings, now there are only 6 that are pumped out by the plant. Okay? No. That's not a good explanation of why the surroundings are less organized. I'll give you one for that in a little bit for this. All right, so are there any questions about this, about what is entropy? And I know it's a little weird, it's a little strange, it's a little bit different than what we've been talking about so far, but are there any questions? Okay, cool. So what does entropy mean in physics? Because it's one thing to talk about what entropy is, but why do we care? How do we calculate this? And how do we actually use it to make predictions? Because that's really what we want to know. We want to start putting this to work. And so you'll see the 2 obnoxious circles, and that's because once that statement comes up, you'll see why those circles are there, but they're there from the beginning, sorry. So systems tend to become more disordered. That is, they tend to have higher entropy. So systems tend to become more disordered. Now, it's a good explanation for why, if you put a glass of water on a table, that eventually all of that water is going to be gone. I don't know if you've ever done that, left a glass of water out on a table for a few days, and then the water's gone. And it's like, it didn't start boiling, right? It doesn't get to a point where that water's boiling, but as water in a gaseous form is more random, than water in a liquid form. And so because of the second law of thermodynamics, it's energetically favorable for it to become more random and for it to turn in from a liquid to a gas. And that's why that happens, even though that glass of water never boils, but all of it will evaporate away. It's also the same reason why you can get huge amounts of evaporation out of lakes and the ocean, even though lakes and the ocean never boil. This is for the same reason. Okay, so that's one application to physics. And here's an equation for us, and here's what all these little different components stand for. So delta G, G is what we call Gibbs free energy. So delta G is equal to H, which is enthalpy, minus T, which is temperature. And I think I probably have, I have all of that here. Sorry, let me just go and get all of these points out so I'm not just saying things. But you can see all that here. So G is Gibbs free energy. H is enthalpy, which is a measurement of the total heat contained in a system. T is the temperature. And then S is the entropy. And so the reason we care about this is delta G is a measurement of whether or not the process is spontaneous, whether or not it will happen without giving energy to that system. So can that process happen without the system absorbing energy? In other words, is it spontaneous? Will it happen even if you don't have organized machinery to make it happen? So if you set a glass of water out, and eventually that water disappears, probably a good indication that water changing from a liquid to a gas is spontaneous, right? Because it just happened. You didn't have to have complex machinery to make it happen. Now, does this make sense? Because now we got a little bit, and you're like, it doesn't ever make sense until we start working out problems. I get that. And then you may be thinking, even once we start working out problems, it still doesn't make sense. I just know where to plug the numbers in. Right? Anybody feel that way? I feel that way. Y'all doing okay? Okay. Am I in your way, Micah? Sorry. All right, so whenever delta G is negative, this process is spontaneous, which means it'll happen on its own. You don't have to supply energy to make it happen. It's actually going to happen on its own, and it will release energy. Looking at this, would you imagine that this is a spontaneous process? Was it happening in the absence of energy? No, we had to put energy into the system to make it happen, right? Energy in the form of sunlight. This is not a spontaneous process. Okay, keep that in mind. Store that up. Store that up as little nuggets of truth. All right, so enthalpy. Enthalpy, total heat contained in a system, it's equal to U. We saw that before, right? U was the total energy in a system. Do you remember that? Total energy, and it was equal to the amount of heat absorbed by the system minus the amount of work done by the system. Do you remember that? U equals Q minus W. Okay, some things coming back. I know, Wednesday afternoons are usually golden times, but I feel like I'm getting very little response from y'all. Maybe y'all just tired of hearing me talk. It's week 3, and you're like, man, there's 3 weeks too many. I get it. All right. So, yeah, we'll come back to that. We'll come back to that in a minute. All right, so we can actually substitute U plus P times V, pressure times volume, in for enthalpy, in for H in our equation. So we have 2 different tools that we might be using. We might use this tool that is delta G is equal to H minus T delta S, or we might use delta G is equal to U plus PV minus T delta S. And so we've got a couple of different tools. Now these are basically the same thing. We're just substituting in U plus PV in for enthalpy. We'll talk about why this works in just a little bit. Just a little bit. Okay. Are there any questions about this? Because now it's a little different, it's a little strange, but we'll start working out some problems. Okay. So what's more random? Okay, got a couple of questions for you. What is more random? Ice or liquid water? What's more random? Is ice more random or is liquid water more random? Okay, think about that. I'm going to give you 10 seconds. Just think about it. Take some deep breaths. Get some good oxygen go into your brain so your brain functions well. If you had like a little energy bar, I'd tell you to take a bite of that. All right, who votes that ice is more random? Who votes that liquid water is more random? Excellent. Liquid water is more random because in ice, it is a solid. The molecules are held in place. In a liquid, there's flexibility for those molecules to move around, which is why liquids take on whatever the shape of their container is. They don't have a constant shape, right? They're more random, more ways in which you can arrange that and still generate the same thing. A fully assembled car or a completely disassembled car? This one we've talked about, a few times. So again, take 10 seconds, think about it. All right, who votes that a fully assembled car is more random? Who votes that a fully or a completely disassembled car is more random? Excellent, right? A lot more ways in which you can arrange the parts of a car if they are not put together making up the car. Do any of you build things? Probably nobody in here builds cars, but maybe you build like Lego, stuff, or you build things out of Connects or things out of Lincoln Logs, right? Okay, so if you just have a big old pile of Legos, there are a lot of ways in which you can arrange those Legos and still have a big pile of Legos. Usually there's only one way in which you could build whatever the object on the box was, right? And then you build it and then you take it apart and start building other things. All right, this one's kind of fun. A star or a supernova? Do you know what a supernova is? It's an explosion. It's when the star explodes and its material is just, propelled through space. Okay, so we have a star or we have a supernova. Think about this. I'll give you 10 seconds again. Think about which one's more random. All right, so who votes that a star is more random? Who votes that a supernova is more random? Excellent, right? Nice thing that whatever the second one is. You're like, give us some more, Dr. Engel. It's always going to be the second one. But yeah, after the star's exploded and its materials just flying through space, that is far more random than having a highly organized star. Right? Okay, so Stephen.
Are these going to be like the questions on the homework?
No. We've got lots of fuel, right? We've got delta G is equal to H minus delta S to use, and we've got delta G is equal to U plus PV minus T delta S. We're bringing it back to calculation problems for the homework. If you liked this last set of homework that were very theoretical, sorry, this week's not going to be like that. So I already told you that the information is on this slide. I'm sorry if that's distracting to you, but here's our question. So if a reaction is carried out in water and has an enthalpy of 457.5 joules, notice that we're measuring enthalpy in joules, and a change in entropy of 4.37 joules per degree Celsius at 55.4 degrees Celsius, is it spontaneous? Is it spontaneous? All right, so we go through and we illustrate all of the things that we are given by the problem. The problem gives us our enthalpy, which is H, right? Tells us that our enthalpy is 457.5 joules. It gives us our temperature. Our temperature is 55.4 degrees Celsius. And it gives us our entropy, which is 4.37 joules per grams degree Celsius. And those are weird units. Joules per grams, not per grams degree Celsius, that's specific heat. This is just joules per degree Celsius. That's a very interesting way to represent randomness. And I'll tell you that these units are there not just to represent randomness, although they do. It's energy per degree Celsius, but it's also a way to make sure that the units work out. The units work out in this equation. So then we have a tool that says delta G, or the Gibbs free energy, is equal to enthalpy H minus temperature times entropy. We also have a tool that says if delta G is negative, this process is spontaneous. And that tool is important because what is this question asking for? It's not necessarily asking for delta G, but it is, right? Because what does the question ask? If it's spontaneous. And in order to know if it's spontaneous, we have to calculate delta G. And then if delta G is negative, then yes, it's spontaneous. Okay? So it doesn't explicitly ask for delta G, but we have to solve for delta G, and we know that delta G is equal to H, which is 457.5 joules, minus T, 55.4 degrees Celsius, times delta S, which is 4.37 joules per degree Celsius. Okay, so let's look at this. Entropy, delta S is positive. And what does that mean? If delta S is positive, what happened? Did it become more random or less random? More random, right? If delta S is positive, our system became more random. That make sense? Okay, so our system became more random, and then so degree Celsius is being divided away here, degree Celsius is being multiplied there, so we can cancel them out. And we end up with 457.5 joules minus this 55.4 times 4.37, which is 242. And so when you subtract 242 away from 457.5, we end up with 215 joules. This has three significant figures here. This has three significant figures here, meaning we need to present our answer in three significant figures. And so delta G is equal to 215 joules. The Gibbs free energy is 215 joules. Is delta G negative? No, it is not, right? It's positive, positive 215. Is this process spontaneous? No, it is not. Right? Delta G is positive, it is not negative, so this process is not spontaneous. Meaning, if we wanted to make this happen, bless you, if we wanted to make this happen, then if it is not spontaneous, what do we need? What do we need to make this happen? How do you make something happen that's not spontaneous? You add energy. So if you want this to happen, since it is not spontaneous, we need to provide energy, even though the system became more random during this process. But it didn't increase enough in randomness to make up for its total heat, the total amount of heat that it had. Okay? We okay here? So again, this material, it's a little weird. It's a little different, talking about randomness and how that fuels spontaneous processes. But the actual equations are not all that difficult to use. And that tends to be true of a lot of the second semester physics. First semester physics, easier to understand, right? You can picture a ball flying through the air, but it's a little bit more complex algebraically to work through those problems. These are more simpler algebraically, but it's a little bit harder to think about because we oftentimes don't think about what's going on when our glass of water on our tabletop evaporates. Unless you're like me. And then I'll show my kids. I'll be like, hey, leave that cup of water out overnight and check it in the morning. And so I'll have them take a little expo marker and draw the line where the water is, and they'll come in the morning and water is gone. And my daughter, she's 6, she suspects if anything happens that I was responsible for it, right? She's like, Daddy, you drank some of my water, didn't you? So no, if I drank some of your water, I would have drank all of your water. But no, it's evaporation. And she doesn't believe me, but we'll work on that. All right. So what is the Gibbs free energy for a system that, sorry, I'd written then and then wrote through, so I just wrote a T over it rather than going and fixing it. Probably would have been easier to just go in and fix it. So what is the Gibbs free energy for a system that has an internal energy of 27.5 joules, a volume of 22.3 liters, a pressure of 1.25 atmospheres, and a change in entropy of 255 joules per degree Celsius at 75.3 degrees Celsius. So this problem gives us a lot of information. It's a little overwhelming, the amount of information that this problem gives us. And so I wrote, let's go through and talk about all of the things the problems gives us. Then we need to talk about our tool for a minute. And an accessory tool that I wrote over to the side here. Atmospheres times liter is equal to joules. All right. So what do we have? It told us that our internal energy, which is U, the total amount of internal energy is 27.5 joules. We have that here. U is equal to 27.5 joules. It tells us that our volume is 22.3 liters. We have that volume written here. Tells us that our pressure is 1.25 atmospheres. Here's our pressure here. Tells us that our change in entropy, which is delta S, is 255 joules per degree Celsius. And finally, it tells us that our temperature is 75.3 degrees Celsius. So that's what we're given. It gives us all of this information, a lot of information. Almost an overwhelming amount of information. So if delta S is positive, is this system gaining randomness or becoming less random? Is it becoming more or less random? More, right? Delta S is positive, so it's becoming more random, which gets you kind of thinking that, well, that's good. If it's getting more random, that's in line with what the second law of thermodynamics suggests will happen. All right, so our tools. We have a tool that connects all of these. Connects U, connects pressure, connects volume. U is internal energy. Connects temperature, connects entropy. And that's this tool here that I wrote down here. Delta G is equal to U plus PV minus T delta S. And then I wrote this tool here, that atmospheres times liter is equal to joules. And by the way, I'm going to tell you this right now, atmospheres times liters is not a perfect representation of joules. It's not a perfect. It would actually be atmospheres times cubic meter that would equal joules, but cubic meter, that's a huge volume. So I wrote something here that is not technically true, but I'll show you even why it can be remotely true. Okay, you ready to see why it can be even remotely true? Okay. Oh, we have some nods. We have some excitement. Okay. Does anybody remember what pressure is? We talked about pressure a little bit last semester. Pressure is equal to, oh wow, need an E. Pressure is equal to force divided by an area. So a force executed across an area. So we'll say force divided by the standard unit, standard international unit for area is meters squared, because the standard international unit for distance is a meter, and then so for area it would be meters squared. We call this a derived value. So pressure is a certain amount of force executed on a certain area. Have you ever heard of pounds per square inch? That's how we measure pressure in a bicycle tire or in a car tire, at least in this country, is pounds per square inch. Pounds is a force, square inch is an area. Pounds per square inch, right? There's pressure. Okay, so this is what pressure is force per square meter, or just any area. How do we measure force, typically? What are the units of force?
Mass times acceleration.
Yep, so mass times acceleration. How do we measure mass? Kilograms. How do we measure acceleration? meters per second squared, right? Do you remember this? Force is equal to kilograms meters per second squared, and then this divided by meters squared. So meters squared is on the bottom of the fraction as well. Okay, so pressure then would be kilograms meters per second squared meters squared. Okay, but that's ugly. We have a meter in both, right? We don't like that. So we're going to cancel this out. And we'll be left with just 1 down here. So pressure is actually in kilograms per meter second squared. We okay with that? What's going on there? So there are our units for pressure. And then I said atmospheres, which is a measurement of pressure, and atmospheres is pretty much equivalent to this, times liter is equal to joules. Okay, and I told you that's not exactly true, but we're going to assume that it's true just for simplicity. And again, I'm sorry if that bothers you. That tool is not exactly true, but it makes solving these problems a lot easier, and it's all relatively speaking. Okay, so we're going to now multiply this not by liters, but instead we are going to multiply it by a cubic meter, which would be another way of representing volume. Okay. And actually would be the proper the standard international way of representing volume would be a cubic meter. But this is a huge volume. 1 cubic meter is 1,000 liters. And a liter is like the size of a bottle of water or a bottle of soda, right? So if you had 1,000 of that, that's a huge volume. Okay? But if we multiplied this by volume, which is what's happening there, pressure times volume, do you see that? See pressure times volume? So that's why we're multiplying this by a volume. Okay, so if we have meters being divided away and a cubic form being multiplied, we can cancel that out and one of these, right? So this would be meters squared. So then this would clean up to be kilograms meters squared per second squared. Now is this looking familiar? Because if you take one of these, and you say kilograms meters per second squared times meters, that is a Newton times meter, which is equal to a joule. Whoa! That's how pressure times volume comes back to energy. You like that? That's pretty cool stuff. You should take a picture of that. Make sure you have a copy of it. Or if you wrote it down as we went through there, that's good too. If you didn't write it down, snap a picture of that. So that way, whenever you solve a problem like this, and you're like, why on earth does pressure times volume equal energy? That's why pressure times volume equals energy. This is why physics is so wonderful. The only thing you need to remember is force equals mass times acceleration. If you remember that, everything else you can derive just by what's going on in the particular problem you're dealing with. And force equals mass times acceleration, that's Newton's second law. I got that nailed. I know Newton's laws. If Newton were still alive, he and I would be buds, and we would talk about his laws together. I don't know if you actually would be friends with Newton, because I don't think he'd speak English. He could learn it, but it'd be kind of hard. Anyways, sorry, that's random. Appropriate, because entropy is a measurement of randomness. All right, so what do we want? This is asking, what is the Gibbs free energy? This is asking explicitly, solve for delta G. Solve for delta G. Well, we just have to go in and plug in what we're given. So delta G is equal to U, our total internal energy, is just 27.5 joules, plus our pressure, 1.25 atmospheres, times our volume, 22.3 liters. And over here in our tools, we said atmospheres times liters equals joules. It doesn't equal, again, this is not true. But for simplicity's sake, we're going to say these units. Now, it is true that pressure times volume equals energy, but the units aren't exactly right. Minus temperature, which is 75.3 degrees Celsius, times, it's missing, times our change in entropy, which is 255 joules per degree Celsius. It's on here on the slide when you get these slides. It's just cut off on the television. I actually ran out of space. It's really crowded on here too. Sorry, I write too big. All right, and so then we just go and we simplify this down. We do 1.25 atmospheres times 22.3 liters, And we're going to use this tool that says atmospheres times liters is equal to joules. And then we'll do 75.3 degrees Celsius times 255 joules per degree Celsius. We'll simplify that down, and then we'll just add them and subtract, right? Order of operations. Algebraically, these problems are simple. As in terms of what's going on, theoretically, these problems are reasonably difficult, right? Just kind of thinking about what's happening. But algebraically, they're fairly simple. And so we end up with delta G is equal to 19,100 joules. This has three significant figures. This has three. This has three. This has three. They all have three. So our answer would be presented in three significant figures, negative 19,100 joules. And so this problem doesn't ask it, but I'm going to ask it. Is this spontaneous? Yes, it is. Delta G is negative. This is spontaneous, meaning this can happen without having to input energy. Okay? This can happen without having to input energy. In fact, this would actually release energy, this process, to the surroundings. So if you were to stand next to this process happening, you'd be warmed by it. Not only could you watch physics in action, but you'd be warmed up as well. It'd be a great joy, right? Unless it were already hot, and then it wouldn't be good to be warmed up any further. Any questions? Okay. All right. This is the last problem we're going to do together, and that should take us pretty close to the time that our class ends, which is 1:40. But we'll save some time for any questions if there are any. So if the Gibbs free energy of a system is 4.56 kilojoules. Wow, that wasn't my phone. I thought for sure that was my phone. Was that you, Micah? No? That was cool. ESPN. All right. So if the Gibbs free energy of a system is 4.56 kilojoules, what is the change in entropy at 65.3 degrees Celsius if the enthalpy is 789.3 joules? Okay, so now this problem gives us delta G is equal to 4.56 kilojoules. And so right here I just did that conversion from kilojoules into joules. And every kilojoule has 1,000 joules, right? That's what kilo means? Yes? Cool. So if it's 4.56 kilojoules, it's 4,560 joules. Enthalpy is 789.3 joules. Temperature, 65.3 degrees Celsius. And then we have our tool. And we're using this tool. Delta G is equal to enthalpy minus temperature times the change in entropy. And then the question is, what does the problem actually want? What does the problem want? And it wants our change in entropy, right? So it gave us delta G. Delta G is positive, correct? Which means delta G, which means this process is not spontaneous. This process is not spontaneous. So you could just think about that there's a pretty good chance that delta S will be negative because it's going to become more ordered, and that's why it's not spontaneous. It's not always that case. It's not always that way, right? Our very first example, we had our system became less ordered, more random, and yet it still wasn't a spontaneous process. Okay, so we know we want change in entropy, so we need to rearrange our tool to solve for change in entropy. First thing we do, we need to try to get delta S by itself. We'll go ahead and add T delta S to both sides. And so now we have delta G plus T delta S is equal to H. Now we'll subtract delta G away. And we'll have T delta S is equal to enthalpy minus delta G. And we have T right now being multiplied to delta S. We want delta S by itself. How do we do it? Divide T away, right? So we divide T away, and we're left with delta S is equal to enthalpy minus the change in Gibbs free energy, all divided by the temperature at which this process happens. Did you have a question, Malachi? Okay. All right, so now we just plug in what we're given into our new tool. We modified our tool to solve for what we want. So enthalpy is 789.3 joules. minus the Gibbs free energy, which is 4,560 joules. You want to make sure you use your measurement in joules and not your measurement in kilojoules, right? Because our enthalpy is in joules. And we divide that by 65.3 degrees Celsius. Now, if we think about this, joules minus joules is going to still give us what as our unit? Joules. Joules divided by degrees Celsius is going to give us units of joules divided by degrees Celsius. Why is that good? Those are our units for entropy. Joules divided by degrees Celsius. Okay? So we subtract that, 789.3 minus 4,560. You get something around negative 4,000 joules. It's a little bit, actually more than that. It's about negative 3,800 joules. Divided by, bless you, 65.3 degrees Celsius, and we get negative 57.7 joules per degree Celsius. This has 4 significant figures. This has 3. This has 3. Our answer needs to be given in 3 significant figures. And so our answer here is in 3 significant figures, and it is negative. And a negative entropy means what? Is it becoming more organized or less organized? Becoming more organized. Remember, if delta S is positive, it's becoming more random, since S is a measurement of the randomness. If it's negative, it's becoming less random, more ordered, more structured, more organized. Okay. So this process is becoming more ordered. We predicted that because our delta G was positive, telling us it was not spontaneous, right? It's not a spontaneous process, so we predicted that it would be getting more ordered, and that's why it's not spontaneous. According to the second law of thermodynamics, can this happen? Can we have a scenario like this? Yes, as long as what is true. When can our system become more ordered? If we input energy. Okay, so if this is something you want to happen, that needs to happen to sustain life, you have to input energy to make it happen. But that's okay. If you wanted to look up what the Gibbs free or what the change in Gibbs free energy is for photosynthesis, you could find that, and it's going to be positive. You're going to find out that it is not a spontaneous process, which is why you have to have an input of energy in the form of sunlight. A cell growing and dividing and making more cells, those are not spontaneous processes, but they happen. It's not against the second law of thermodynamics. It just tells you have to put in input energy to make that happen. And you find out that organisms can't live without energy input. Plants get their energy input from sunlight. We get our energy input from plants or eating things that eat plants, or both, right? If you want to have a nice omnivorous diet, eat a little bit of plants, a little bit of stuff that eats plants, or a lot of plants and a little bit of stuff that eats plants, or a lot of stuff that eats plants and a little bit of plants. However you want to do it. However you want to do it. Actually, you could live by just eating plants. You usually have to do some kind of a vitamin supplement, some kind of that includes some of the amino acids that you don't absorb well out of plant material. But it's doable. It's doable. So are there any questions about this? Yeah, Josh.
If ice is the more organized
Yes.
form of water,
Yes.
so that means it needs to absorb energy. Water needs to absorb energy to turn to ice.
So you have to realize as water changes state, it is not a chemical reaction. And so you wouldn't measure it with like Gibbs free energy. So Gibbs free energy used to measure chemical reactions. A change in state is not a chemical reaction, it's a physical change. So since water has not changed in any way, usually wouldn't represent that with Gibbs free energy. But to address your question, so if entropy, so delta S, is decreasing as it moves from water to liquid, right? So delta S is negative if you're going from liquid to a solid. Then in order for that to be a spontaneous process, which by the way it isn't spontaneous for water to go from liquid into a solid, you would need to have your total heat in the system would need to be more negative than what you're getting from the drop in entropy. And so in order to have that possible, you'd have to lose heat, is what I'm getting at, right? Your delta H is going to have to be negative. You're going to have to lose total heat of the system, and you're going to have to lose more than the amount of drop in entropy moving from a liquid to a solid. And so you'd have to drop temperature. And that's why the only way to convert from a liquid water to a solid water is if the temperature drops below the freezing point. It doesn't happen just at, a constant temperature, unless that temperature is below the freezing point of water. At which point your system, that is your water, is losing heat. Your H is becoming negative, and becoming negative faster than your S is becoming negative, if that makes sense. Yeah, so that's how you get around it. So you'd have to lose energy from the system. So you'd have to, so if you wanted to make water go from a liquid to a solid without that drop in heat, then yes, you would have to put energy in to make it happen, to form those bonds. And so you could make that happen. Like you can form water at high temp or form ice at high temperatures by inputting energy, forcing the hydrogen bonds to lock in place and to form a crystalline structure. It's not the way it happens. Yeah, not the way it happens. It's a good question though. Any other questions? That was actually a really good question, Josh, by the way. It's like, okay, well, we've got this process, delta S is negative. Does it require energy to make it happen? And that would be only, yes, but only if delta H is not more negative than delta S is at any given temperature. You also have to realize that the temperature at which that happens is at 0 degrees Celsius. And so 0 times delta S actually ends up canceling out, and then so your delta H just needs to be negative. You have to lose heat in that system. All right? Any other questions, thoughts, concerns? So I'll send these slides out. They've already got the solving for these practice problems that'll have the homework attached to it. It'll have quiz 4 attached to it. If you have any questions as you're working through those, please ask them. If not, I will talk to you a week from now. And again, we'll do lab 5. And we'll be working with trying to test or trying to see how close we can get to what we would predict would happen. Right? We'll have a known mass of water. We'll have a known mass of some metal. We'll heat that metal up to a very specific temperature, put it into water at a very specific temperature, and see how closely it matches what you would predict from the specific heat of water. We'll have some good times. Really, we'll sit around and we'll wait and we'll talk, All right? Well, cool. Have a wonderful day. Enjoy the rest of your Wednesday.